All right, so let's get this started. Today we have a special speaker. This is Alex Psomas. He's coming to us from Berkeley. He is finishing up his PhD with Christos Papadimitriou. And today he's going to tell us about controlled dynamic fair division.
Hello everyone, it's great to be here. I'm a huge fan of the work people do in CMU. So this is going to be a joint work with Eric Friedman from UC Berkeley at ICSI, and Shai, who's a postdoc at Caltech. So my full name is Christos Alexandros Psomas. I go by Alex. I like to joke that the Christos is silent. Okay, so today I'll be talking about controlled dynamic fair division. Okay. So let's see a couple of fair division examples. So classic fair division example is cake cutting. So you have a cake, and you have agents that have preferences over the cake. So Alice only likes strawberries, Bob only likes chocolate, Kostis wants a proper slice, David likes the top half. Yeah? And our job is allocate this cake, give everyone something in a way that is fair. Okay? And now what fair means, it's up for debate. Two very popular notions of fairness in this setting is proportionality, which means that everyone gets at least an nth of what they think the whole cake is worth. Another very popular notion of fairness is envy-freeness, which says that in the final allocation, no one wants to switch pieces with anyone else. Here's another fair division example. You might have two computational resources, like 1 unit of CPU and 1 unit of RAM. And now the agents have a little bit more complex demands. They can say, okay, Alice wants half a CPU and 1 unit of RAM. And I want you to read this as for every unit of RAM, she needs half unit of CPU. You know, Bob wants 1 CPU and 0.4 RAM, Kostis 0 CPU and 1 RAM, David wants 1 CPU and 0.9 RAM. Okay, so for every unit of CPU needed, he needs 0.9 RAM. Okay? And now again, we want to find an allocation of these resources in a way that is fair. And again, what fair means, it's up for debate. Two very popular notions of fairness in this setting I'm describing is DRF and competitive equilibria for equal incomes. I'm not going to go into more details. Time permitting, maybe I will. Okay? But don't worry too much about it. I just want to say that fairness is a big topic. There's a lot of things done. For most of this talk, I'm going to be talking about a very, very simple model of fairness. So I'm going to have just 1 unit of resource, and everyone's going to be homogeneous. That means that in everyone's eyes, this is the resource. This is the unit. So if you get an x fraction, you are happy x. Your utility for an x fraction is x, and that's that. The first x, the middle x, broken up, doesn't matter. Okay? And we want to divide it fairly between n agents. Simple enough. So for 4 agents, arguably the only fair solution is everyone gets 1 over 4. Okay? So fair means everyone gets an nth. Okay? I hope I have no counter arguments to this. So conclusion, we're done. Okay? That was easy. Cool. So I have this solution for 4 agents. And what I'd be interested in is what happens as agents come and go. So you have this solution, 4 agents are there, everyone has a 4th. And now, lo and behold, the 5th agent arrives. Again, for 5 agents, a fair allocation of this resource is everyone gets 1 over 5th. So everyone has 1 over 4th. You need to arrive at a situation where everyone has 1 over 5th. How do you do that? You just reclaim everything you did and reallocate it. Okay? Or another way to do it is everyone gives up like 1 over n plus 1 fraction of what they have and give it to the new person. Okay? So you take everything back, you give it, you reallocate it, everyone has a 5th, now you're at a fair solution. Okay? Simple enough. So if you have 1,000 agents and everyone has 1 over 1,000, which is the fair thing to do, and one more agent arrives, again, the only fair thing to do is take everything back, redistribute it. Okay? Take everything back, redistribute it. But if these are computational resources, so if this is literally a CPU or RAM or something that I'm using to run tasks on, this could be very disruptive to the users. Okay, so this is not just a theoretical fantasy. So here's a quote from a systems paper. So in a scheduling application, they had exactly this problem. So the offline scheduler, the optimal offline scheduler, was too disruptive. So if you wanted to have the optimal solution at every step, you would have to be very disruptive. Okay, and that was an issue. So this is, I don't have all the authors. This is a paper from Ali Ghodsi, Ion Stoica, Matej Zaharia, and Scott Schenker. They're all from Berkeley. But these are systems people, and this is a real problem they faced. Okay? In fact, the reason I was interested in initially was from working on a systems project. Okay? So we want to fairly divide resources as people come and go, and our problem is if we want perfect fairness at every step, we are too disruptive. So we want to explore the trade-offs between disruption and fairness. So you have a fair division problem. The first thing you do, you go to Ariel's webpage. And lo and behold, if you want no disruptions, paper by Ian Cash, Ariel, Prakacha, and Nishar Shah, consider this case of no disruptions. So if you limit yourself to not disrupt anyone, and for many resources, we understood fairly well what are our limitations. So in that paper, they define, among other things, the appropriate notion of Pareto efficiency. So it's called dynamic Pareto efficient. And in some sense, in that setting, the thing that makes sense to do is try to beat, if you have k agents and n people are going to arrive, you should be trying to beat a mechanism that uses a k over n fraction. Okay, that's something the best thing you can do if you're not allowed to disrupt anyone. Okay, so in that paper they explore the limitations of the setting, and they have impossibility results, and they also design mechanisms that satisfy a number of desirable properties. Okay, so this is in the no disruptions case, and the downsides to this approach is, number one, I need to know n. So I need to know how many people are going to arrive to run these mechanisms. And number two, even if I know n, maybe maybe n is 1,000, but maybe most of the time I have 10 people. So I'm inherently very inefficient in that situation. I'm using 10 over 1,000 of the resources, because if I use more, when 1,000 people eventually come, I'm going to be stuck with something really, really unfair, since I'm not allowed to reclaim any of the resources I allocate. Okay? So in this paper, I want to talk about some interpolation between disrupt everyone all the time, which leads to perfect fairness, and disrupt no one. Okay? So let me keep tabs on time. So something in between is going to be controlled disruptions. So the first thing I'm going to define is I'm going to create algorithms that take the following input. The input to my algorithm is going to be a vector. And the vector is going to tell me how many disruptions am I allowed. Okay? So when the ith agents arrives, I'm going to look at the ith index, and that number is going to tell me how many agents I'm allowed to disrupt. Okay? And for now, again, we're going to consider a homogeneous resource. So a unit resource, everyone wants the same thing, uniform 0, 1. Okay? So, and I'm going to call the people I disrupt donors. Question?
Do your agents depart?
I'll get into that. That's a great question. So the question was, do the agents depart? I'll answer that in 10 slides. Okay? So here's an example of my, sorry, go ahead.
So I guess you only get one control vector.
Oh, let's see if after this slide. So here's an example of a control vector. This is a control vector for 5 agents. This is telling me when the first agent arrives, I'm allowed to use 1 disruption. This is kind of a corner case. When the second agent arrives, I'm allowed to use 1 disruption. This is what this 1 means. Question?
Is this like a stream, or do you get it all before any of the regions?
I'll also answer that. So for now, let's think of it getting it from the beginning. So from the beginning, I'm getting this as an input to my algorithm, and I'm going to try to do the best I can with it. Okay? So this second one means I'm allowed one disruption when the second agent arrives. This one says I'm allowed one disruption when the third agent arrives. This 0 says that when the fourth agent arrives, I'm not allowed to disrupt anyone. This 2 says when the fifth agent arrives, I'm allowed 2 disruptions. Okay, that means I can disrupt, I can take resources back from 2 agents. Question?
Is the underlying assumption that these agents are arriving in the order that like the first agent comes before the second agent, or is it like any of them could come at any time?
So the question is, are the agents coming in order?
The first one and then the second one and the third one. You don't know when, but.
Yeah, so they're all identical to me. So it's kind of anonymous because they all have the same utility. They want the same. So this question is a little bit more relevant when we go to a more general setting where people have actually different demands. But for now, for the homogeneous resource, it's the same. Okay? So I only care about how many people I have. That defines what's the fair thing to do. Okay? So this is going to be the input to my algorithm. And of course, an algorithm is feasible if it satisfies these constraints. So that means that if I have an allocation for 3 agents, when the fourth agent arrives, I cannot take resources back from anyone. If I have an allocation for 4 agents, when the fifth one arrives, I'm allowed to reduce the allocation of 2 people. Okay? So this is going to be my design space in some sense. And now I need a way to evaluate solutions. So I'm going to need one more definition before I show an example. And that definition is the fairness ratio. So if I have an allocation, the fairness ratio of that allocation is basically the smallest utility over the optimal thing to do. Okay? So if I have 3 agents and I have an allocation 2 over 5, 2 over 5, 1 over 5, the fairness ratio of this allocation is the smallest share, which is 1 over 5, over the optimal allocation, which is a third for 3 agents, a third each. So the fairness ratio of this allocation is 3 over 5. Okay? And the fairness ratio of an algorithm is basically the worst fairness ratio across all allocations it outputs. Very similar to competitive ratio for online algorithms. Okay? Let's see an example. So say the control vector was 1, 1, 1. Okay? Here's an algorithm that's feasible. When the first agent arrives, we give him everything. Okay? So the share is 1. The optimal thing to do is 1. So the fairness of this allocation is 1. Okay? When the second agent arrives, we're allowed 1 disruption. Well, there's only 1 person there, so we can disrupt them. And we can take back half the resource, and we can go to an allocation of half and half. Okay? So the smallest of the 2 is half. The optimal in terms of fairness allocation is half-half. So the fairness in this case is 1. Okay? So now a little bit more interesting. When the third agent arrives, I would like to go to the allocation a third, a third, a third, but this is impossible with only 1 disruption. But something I could do is disrupt this person down to a fourth and go to an allocation of half, a fourth, a fourth. So now the fairness ratio of this allocation is the smallest share, which is a fourth, divided by the perfect thing to do, which is a third. So the fairness is 3 over 4. And the fairness ratio of this algorithm is the smallest number, which is 3 over 4. Questions?
Just to clarify, given this control vector, you're implicitly knowing exactly how many agents will arrive?
Yes.
Okay.
And I'll take that assumption out a little bit. Okay? Another question? Does everyone understand my design space, what I'm trying to do? Question?
So you're only judging your algorithm by the smallest ratio it ever gives?
Yes.
So it would be better for you to, while there aren't very many agents, not use everything, but like.
Good, good. Yeah, so very good. I'll go back to that a little bit. So the question was, or let me rephrase a little bit. So it could be, this algorithm has the same fairness ratio, even if, this was not all allocated. I'm just looking at the smallest possible number in there. So even among allocations with the same fairness ratio, there could have been, better things to do, but I'm not going to explore that much. I'm going to touch on it a little bit, okay, in terms of Pareto efficiency or things like that. Okay. So our goal would be, given a control vector, design a mechanism that gives a good fairness ratio. Okay, that's going to be my goal. Something I could do even better is try to give an algorithm that's instance optimal. So I could try to find the best fairness ratio for a given control vector, for a finite control vector. And something better I could do is even go for infinite control vectors. So try to provide, guarantees for families of control vectors. Okay? Cool. I'm going to be doing all of these. So, and other extra things I might ask for is accommodate departures. So what happens if people start going away? I could ask for my allocation to be Pareto optimal at every step. So I could ask to be using all of the resource all of the time. I could ask for other guarantees. I could ask for bounds and enviness. I could ask for multiple things. Okay? I'll be touching on the first two. So we saw this example. If the fairness ratio, if the control vector is 1, 1, 1, first agent gets everything. Second agent gets half, half. Third agent gets a fourth. So I get to an allocation half, fourth, a fourth. And these are the equivalent fairness ratios. Here's something I could do instead. I could try to introduce a little bit of unfairness earlier so I could do better at the third step.
Wait, so
Question?
are you rating it by the minimum fairness at a single step?
Yes. So the fairness ratio of the algorithm is the worst number in this column, which is 3 over 4. Okay?
So it's the worst at like any time, like
Yes.
the most mistreated person.
Yes, yes. So across, so it's a minimum over steps, minimum over people. Good. So I can try to introduce a little bit of unfairness earlier in the game, try to do better. So here's something you could do. First agent comes, get the whole thing. Second agent comes, and instead of going to half-half, you could try to go to a third, 2/3, aiming for getting perfect fairness at the third step. Okay, so go to a third, 2/3, and then when the third agent eventually comes, you're allowed only one disruption, so you go to a third, a third, a third. Okay, so what are the fairness ratios of this algorithm? In the first and last step, I have a fairness of 1, because I was doing the best possible thing. In the second step, the smallest share was a third. The best thing to do, the optimal fairness, was half. Therefore, the fairness ratio is 2/3. So the fairness ratio of this algorithm is 2/3. So I'm doing worse, right? 2/3 is smaller than 3 over 4. So this is a worse algorithm than this one. Okay. There is something better to do. I'm going to show you the optimal thing to do for this specific control vector now. So here's the question.
So suppose someone arrives in the ith step,
Mhm.
then any reallocation, could you maybe give some stuff to some guy who arrived?
Yes.
Like the I-1
Yes, great question. So giving to people is free, taking away is expensive. So I have no limitations. Maybe I take from one person and give to everyone else and the person arriving. My limitation is only in taking. I'm making the assumption that giving you resources doesn't cost you anything, taking you resources costs you. Okay? Good question. And in fact, this is going to become very relevant when I have departures.
Wait, okay, so maybe missing something. What prevents you from just like giving the thing to one guy and then when, or just like withholding everything and when the last person arrives, you.
Oh, because then the fairness ratio for every step until the last one is going to be 0.
Oh, so you care about fairness ratio at
Every step, yes, yes. So it's a minimum over steps, minimum over, share over.
Do you also have to like always allocate like the entire?
Not yet. There are some limits to that. I'm going to explore that. So that's what Pareto optimal at every step was earlier. Okay. The question was if I have to use the whole thing at every step. I'm going to touch that in a little bit.
Yeah, sometimes.
I mean, I now will, but generally I can't. I'll get into it. Okay. So here's the optimal solution for 1, 1, 1. First agent arrives, they get the whole thing. Okay. Fairness 1 in that allocation. Second agent arrives, I split it into 3 over 7, 4 over 7. Okay, that has a fairness ratio, so the smallest of 3 over 7 and 4 over 7 is 3 over 7. Perfect thing to do is half. Fairness of 6 over 7. Right? Okay, last agent arrives. I split the 4 over 7 into 2 over 7s. The smallest number here is 2 over 7. Perfect thing to do is a third. Fairness ratio 6 over 7. Fairness ratio of this algorithm is 6 over 7, and that's the best thing you could do. Okay? Questions?
Is that the best even without the Pareto optimal?
Yes. I will show that too. The question was, is that the best you can do even if you're not restricted into using the whole resource all the time? And the answer is yes. Okay, good. So now let's see an algorithm to figure out these things. So let's pretend for now that I'm given the control vector, but I'm also given this best number. Okay? So there is some number, some sigma that's the best for a control vector. Assume I'm given that. And I'm gonna solve the problem assuming this, and then I'm also gonna show you how to find this sigma. Okay? So I'm assuming I'm given a control vector now and the best possible fairness ratio for that control vector. And my algorithm is called skip, so it receives these inputs, and it works as follows. So when at the kth arrival, if you're allowed d disruptions, you just take the d richest people and you decrease them to sigma over k. And you also give the new agent sigma over k. Okay? So the kth person arrives. My control vector is telling me you can only take resources from d people. I pick the d ones with the highest share, reduce them to sigma over k, give the new agent sigma over k. Okay? Notice that there's k people on the kth step. So the perfect fairness is 1 over k. So if the smallest one is sigma over k, that gives a fairness ratio of sigma. Okay? So let's see it run. So for this control vector, 1, 1, 1, 0, 2, here's what this algorithm is going to do for some sigma. So first agent arrives, they get sigma. Second agent arrives, well, I'm allowed 1 disruption. So this sigma will go down to sigma over 2. New guy will get sigma over 2. So I'll get sigma over 2, sigma over 2. Okay? Third agent is about to arrive. I'm allowed 1 disruption. So I can't decrease both of these. I can only decrease 1. I'll pick a sigma over 2, go take it down to sigma over 3, because the third step. New agent gets sigma over 3. So I go to this allocation. Okay? Next step, I'm not allowed to disrupt anyone. So all of this will remain. And the new agent will get sigma over 4. So I go to this allocation. Sigma over 2, sigma over 3, sigma over 3, sigma over 4. Last step, I'm allowed 2 disruptions. So I take the 2 highest ones, these 2, sigma over 2 and sigma over 3. Take them down to sigma over 5. New agent gets sigma over 5. So I take sigma over, the last allocation is sigma over 3, sigma over 4, and 3 sigma over 5s. Okay? That's going to be how this algorithm runs. Okay? So now the only thing that's left to do is figure out the sigma.
So
Question?
You just pick like the maximum on the 5 steps, and that's how you get it.
The minimum, but let's see.
Well, you can sum up on each.
Exactly. Excellent. So notice that I only have 1 unit of resource to allocate. So it better be that the sum of these rows is at most 1. Okay? So I'm summing up the rows. So this row sum up to sigma, 7 sigma over 6, 17 sigma over 12, 71 sigma over 60. Believe me? Okay? So this sum better be less or equal to 1. You know, by, I don't know, middle school math, that gives you an upper bound on sigma. And you just take the smallest upper bound. Happens to be 12 over 17. Notice that the 6 over 7 that appeared earlier was the optimal one. And that's it. That's the best thing you could do for any control vector. For this control vector, it's 12 over 17, but that's how you figure out what to do for any given finite control vector. And that's it. Okay? Any questions?
Is there a simple way to see why this is optimal? I mean, certainly for this scheme, this is the right way to find sigma. But I mean, is there like, but why is this in fact the best you can do even under?
Good. So the proof goes through basically if you give me any other algorithm that is feasible for that sigma, I can do better with this one because it's the one that uses the least resources the intuitive way. If that makes sense. So it's the one that achieves this fairness ratio and being very minimal in the amount of resources it's using, so I can kind of simulate everything else with it. Cool? Great.
So it's just like a simple exchange argument, you have some other algorithm, and you look at the first point where it differs, and you twiddle it, or it's a little more complicated than that?
It's some inductive argument like that, yes. So you do some point-wise majorization, you look at the vectors they output. Some point-wise comparison or something like that. Since I'm only judging it by the smallest at every step, I can do that argument without too much pain. Okay, cool. So let's see this run back to our 1-1-1 example to notice something that a lot of you already pointed out. So the best sigma there was 6/7, right? So running this algorithm would mean this. First person comes along and they get 6/7. So I'm leaving 1/7 on the table. Okay? So first person gets 6/7. Next person should get, sigma/2, which is 3/7. Last person should get sigma/3, which is 2/7. So this would be how this algorithm runs, the way I've described it. And notice that it was not Pareto optimal. In the first step, I was not using, or on the second step too, I was not using all of the resource. So a question you could ask is, when can I get optimal fairness? So when can I get the optimal fairness for a given control vector and at the same time be Pareto optimal at every step? And the answer is very clean. It's if and only if there's no 0. So if your control vector has no 0, both these things are possible at the same time. Okay? A little asterisk, except in the first coordinate. The first coordinate doesn't really matter. It's a technicality to simplify notation. Okay? Good. Another thing a lot of you pointed out. Everyone okay with this? Another thing a lot of you pointed out is, how do we do disruptions? So say you are at some allocation that looks like this. Sigma/3, sigma/4, sigma/5, sigma/5. Somehow you got there from some other previous allocation, right? Using some number of donors. So this step is possible using some number of donors. So we could show, I'm not going to show it, that if this is possible, then no matter who departs, so it could be this sigma/5, it could be this sigma/3, also this is possible. So I can use the departing agent's resource, the departing agent's share, plus whatever I have in my bank, and get to this allocation. And I don't need any disruptions. So when agents depart, I'm only using the bank, what I had on the side that I wasn't using, and the share of the agent that was leaving. And I'm just giving it back to people. So if this step is possible, one can show that the other one is possible too. Okay? Great. So my algorithm is doing pretty well so far. I'm feeling good. Here's what any questions so far? Good. So what I would like to do next is maybe start providing guarantees for families of control vectors. So maybe it doesn't mean much to you that I can do the optimal thing for a given control vector. Maybe something you would like to know is, how would I do for, if the vector was all ones, arbitrarily large, or if the vector was all Ds, or if the vector had at most 5 consecutive zeros, things like that. So for the next of the talk, I'm going to try to answer these types of questions. So how well am I doing, in terms of numbers for certain families of control vectors? So let's start with the all ones vector. So for n equals 2, you could do the best. For n equals 3, we saw you could do 6/7. And kind of for n equals 100,000, you could do 0.72. What that means? So I'm going to show you how to do this analysis, basically. Okay? Everyone okay with what I'm going to do now? Cool. So the algorithm works as follows. This arrow should be pointing here. Okay, so let's see. It's easier to do it here. So in the first step, I get a sigma. I'm allowed to use one donor. When the second agent arrives, this sigma becomes sigma/2. And the new agent gets sigma/2. One more agent arrives. One of these goes down. It becomes sigma/3. The new agent gets sigma/3. Right? One more agent comes. The sigma/2 becomes sigma/4. The new agent gets sigma/4. One more agent comes. The sigma/3 goes away, becomes sigma/5. The new agent gets sigma/5, and so on. Okay, does everyone see what's happening? The sigma/3 goes away, becomes sigma/6, sigma/6. So look, I'm at an even step, and I have 2 sigma/4s, 2 sigma/5s, 2 sigma/6s. Okay, so generally in the even steps for the all one vectors, I can can maybe try, I can characterize the allocation exactly. Okay, very lucky. So for 12, it's something like that. 2 sigma over 7s, 2 sigma over 8s, 2 sigma over 9s, all the way to 2 sigma over 12s. So now, okay, what did we do earlier? We took the sum, right? So this is a sum. This is 2 sigma, and the sum from I equals x plus 1 to 2x of 1 over I. Okay, blah, 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 harmonic analysis. 2 sigma, log 2x minus log x, which is log 2. So 2 sigma log 2, which is sigma log 4. This better be less than or equal to 1. So the optimal fairness ratio approaches 1 over log 4, which is 0.72. Okay? Questions? Good. And one can show something slightly more general. So if the fairness ratio is all D's, it's easier to read like this. Sorry about that. It's 1 over D plus 1 log D plus 1 over D. Okay? Notice that if I plug in D equals 1, I get 2 log 2. Okay? And the proof, you need to be a little bit careful, but again, it goes through exactly pinning down the allocation at every single step. Okay? Very important. Okay? Good. So I'm done with these families of vectors. So if you promise me that you're going to give me something that looks like this, I can play ball. Right? I can guarantee you something. So now, the next thing I want to talk about is maybe I want some guarantees when I start getting zeros. Okay? So maybe I would like a guarantee if I have, say, at most 5 consecutive zeros. It might be something you're interested in. So it could be, 1, 5 zeros, 1, 5 zeros, 1, 3 zeros, 1, 1, 1. Something with at most 5 consecutive zeros. Okay? Well, let's see what the allocations look like pictorially. They look like this. This may not mean much to you, but this is what it looked for the all ones. Okay? So the all ones, you have a nice logarithmic harmonic thing. This is for 5 zeros. This is for 10 zeros. Okay? So in some sense, if the analysis goes through pinning down exactly what you're doing at every step, you're going to have a hard time. Okay? Because the allocations do not look very structured or very complicated. In fact, notice that the asymptotic is different than the earlier one. And it changes, some of them, you can't see it clearly, but some of them are always below this asymptotic, some of them aren't. It's a whole mess. Okay? But I'm going to provide guarantees for these types of vectors, but they're not going to be tight. Okay? And this is my lame excuse. Complexity. Okay? But let's do a show of hands first. So what do you think is going to be the guarantee I can give you if the input vector has, at most 10,000 consecutive zeros? So you're allowed to give me a control vector with 10,000 consecutive zeros, not 10,001. 10,000 consecutive zeros. So it could be 10,000 zeros, 1, 10,000 zeros, 1, 10,000 zeros, 1, going forever. What do you think my guarantee can be? So, A is 1 over 10, B is 1 over 100, 7 over 1,000, 1 over 1,000, 1 over 10,000. Remember, for no zeros and no ones, it was 0.7, approximately 0.7. So who thinks A? Who thinks B? C? D? E? Well, I guess everyone's wrong.
Really?
Yeah. Weird, right? Question?
Do you ever consider it's exactly 10,000 zeros, not less than?
It could be less than.
Okay.
Yeah. It's at most 10,000 zeros consecutively. Okay? You're not allowed. The only thing you're not allowed to do is put 10,001 consecutive zeros. Anything else is fair play. Okay? So the actual guarantee for at most C consecutive zeros is upper and lower bounded by these things, which may not mean much to you. That's why I showed you the example first. So our lower bound is harmonic number of 2C plus 3 minus half 1 over. our upper bound is harmonic of c plus 1. Again, if you don't know what harmonic means in this setting, you know, h of n is the sum of I equals 1 through n, 1 over I. So if you plug in c equals 10,000 on the right side, you're going to get something approximately 1 over 10. Okay, that's what I did in the previous slide. Okay, my conjecture is that this number is correct. I don't know enough harmonic analysis, I guess.
Yes, I don't understand what's wrong with my argument I had in mind for E. Right? So I'm putting the 10,000 zeros as the first 10,000 rounds. I can disrupt anybody for 10,000 rounds.
Mm-hmm.
And then, I mean, if I give anybody more than 1 over 10,000, well, okay, maybe it's not exactly, but the thought was that I can't give anybody more than something very different than 1 over 10,000, because otherwise, you know, because I can disrupt anybody, by the time I get to the 10,000th person, I won't be left with any resource to give that person.
So the question was, if I put all the zeros at the beginning, then I shouldn't be able to do 1 over 10,000. Because
but the point is that you're comparing it to the minimum possible. Like if you have 10,000, like there's no way to give them more than the small.
Yeah, I could start doing smaller.
So Alex, given the bound, now it seems a bit clearer what the algorithm is, right? Sigma over 2 for the first guy, sigma over 3 for the next guy.
Yeah.
Sorry, sigma over.
So sigma over 1,000. So the last guy is getting sigma over. You're thinking of 1 over 10,000 as the fair thing to do, but if I give 1 over 20,000, I'm a 2 approximation.
Sure.
Right? So that's where I'm.
Okay, I see what I was doing.
Cool. Good. Great question. Cool. How am I doing time-wise? Okay. So I'm going to mention a little bit about multiple resources, and I'm going to conclude. So in multiple resources, we saw that the demand started becoming a little bit more tricky, right? So Alice said 0.5 and 1. Bob said 1 and 0.4, so on and so forth. So something crucial to understand here is for me to decide what's fair, I need to know these demands. Okay? So now I have a designer choice. Do I know these demands in advance, or do I not know these demands in advance? Notice that this wasn't a problem earlier because I just assumed the cake was homogeneous. Like if I gave you an x fraction, you were cool. You had the utility x. But now I need to know what you want to decide what's fair. So you can ask, well, clearly if I know everyone's demands that's going to come, I can do better. So do I know it or do I not know it? Am I clairvoyant or not? Yeah. Well, the first theorem is going to be bad news. So the theorem is going to be that if I know the agent's demands, and if I have, you know, let's do a very generic fairness. So instead of fixing my notion of fairness as 1 over k or something like that, I just want upper and lower bounds at every step on the utilities. So I'm just telling you, okay, so it better be, you know, you better not use many disruptions. And at every step, I want all the utilities to be between L and U. Okay? And L and U might be different at every step. And so just give me a fair division for, say, the control vector 1, 1, 1. So this problem is NP hard, even for binary demands. So even if the demands are 0, 1, and there's 2 resources. Okay, which means that you cannot solve this problem optimally. Regardless, we have some results. I'm going to conclude. But so, what do we talk about so far? So we showed the skip algorithm, instance optimal. I can figure out the best fairness if I have finite or infinite, you know, control vectors. I can be Pareto optimal at every step sometimes. I can do departures. I show some bounds for the general case where I had zeros and whatnot. So for a certain family of control vectors, I can show some general bounds. I mentioned that the general, for multiple resources, you go into an NP hardness. Sorry, go ahead.
How would the proof go for this NP hardness?
For this NP hardness? So it's a since I know everything, there's no really online aspect to it, only the disruption part. And it's a reduction from subset sum, if that means something to you. Yeah, or some, you know, version of subset sum. The appropriate version of subset sum. I'm really using the L and U's in a certain way. So I don't know if you fix a notion to be something other. Sorry, I'm going to go. Something I didn't talk about today was upper and lower bounds for dynamic DRF. So if you fix your notion of fairness for many resources to be dominant resource fairness, which if you know what it means, good. If you don't know what it means, it's something popular. It's one of the two most popular things. We can kind of use the single resource to provide some guarantees. So we can black box a single resource algorithm to give some guarantees on the fairness. So, okay, what are research directions that I think are interesting? So you can try to close the gap for a single resource, or you can try to consider other families of control vectors. So this is in order of how I think they're interesting. So you can try to do better algorithms for multiple resources. So currently, if I want to do multiple resources, I'm black boxing my single resource algorithm. So for every resource, I'm using my single resource algorithm, and I'm doing some smart way to make sure I don't disrupt too many people. I don't know anything else to do. Another question that I think is very interesting is modeling incentives. So I'm not really, the incentives part never came into play. I just assume everyone's going to tell me the truth. I mean, there's no truth to give in the homogeneous case, but so I don't know what that would look like. And the last thing is just this control disruption thing can be applied to any problem you want. So in fact, Anupam here has a paper for, it's online algorithms, I guess, but so you're trying to maintain a minimum spanning tree, and vertices arrive online, and you're allowed to change your solution by one edge at a time, or something like that. So it's not online algorithms in the sense that once you commit forever to the solution you're doing right now, maybe you're allowed to disrupt it a little bit, and that is very appropriate in some settings. One of these settings is scheduling. That's what this paper was motivated by. Generally, you can do other things. That's it. That's all I got. Thanks. Questions?
Are there any questions?
Go for it.
Okay, sorry. So for the NP hardness resolve, you said the reduction was from subset sum, which means that it's not strongly NP hard.
That's right.
So then if you allow yourself to use like pseudo polynomial time, for example, is there a way to do it, or
I don't know. I don't know. That's a great question. I don't know if you want approximations. I don't know, but best fairness you can do. Yeah. The question was, can I start doing approximation? Can I start doing like classical algorithm design tricks like p-tasses, f-p-tasses? I don't know the answer to that.
Does the order of the control vector matter?
Yeah.
So if you had a worst case ordering, what would you be like if you didn't know the order in advance, let's say, but you knew n as the number of people coming in?
Good.
Is there something you can say about that?
So then in that case, I mean, of course it would be the all zeros, right? So you have to restrict the family a little bit.
Yeah.
So if you restrict it in various ways, I can tell you the answer. So if you restrict it to have at most C zeros, I would just take my bound. In fact, that's how we started it. Say I have, n, I'm allowed at most 5 consecutive zeros, do your worst. So that's the bound we're trying to do. Another question you can ask is, what's the best? Because maybe you can think of the disruption vector as decided by you, the designer. So you can say, well, what's the best I can do, not the worst? That also makes sense. I have no idea what the answer is.
Disrupt everyone all the time.
What?
Disrupt everyone all the time.
Okay, well, with some restrictions. Okay, that's a good point.
Yeah.
Exactly. So that's great. So you could have some amortized analysis as well. You could have you have 10 disruptions. Go. Do your best. I don't know the answer to that.
Yes, it seems like so obviously disruptions you can also view them as being unfair to agents. Like if you're the donor over and over again, that can be seen as unfair to you, even if ultimately your shares are really good. So would it make sense to add a constraint of, an upper bound how many times you're allowed to disrupt agents? So like your algorithm seems like it cycles around, right?
Yeah, it's doing a round robin, so it's fairly okay with that aspect, but I don't know.
That algorithm, right?
I don't know if you put it as a hard constraint, what would happen. That's a great question. Yeah. In fact, this makes a lot of sense in the multi-resource. So that's something that could happen. I don't know. Yeah.
Would it make sense to, instead of having, saying how many instructions you're allowed, not just, right, we were talking about you have the vector, but you could also have just a number of how many disruptions. But would it make sense to just say, every time you disrupt, you pay some cost to minimize
yeah.
that? Is that, do you think that would lead to very different?
I think it will lead to very different results. Maybe. So I know that in the scheduling literature, even though there's no such fairness flavor that I'm having here, but I know that people do write papers on things like, what's going to be my flow time objective if I have a bound on my disruptions. So I know people study things like that and they get very different results, very different algorithms. But if you add fairness, I don't know. But yeah, I would guess that they're a little bit different if you pay for a disruption. Good, but great question.
Any other questions?
So this might actually be a similar question, I don't know. If you think about a job as, requiring a certain amount of resource time in order to complete, this is getting back to the question about departures.
Okay.
If I'm allocated less of the resource than I need, it's going to take me longer to complete, and then I'm going to be taking up this resource for a longer time, which prevents other people from getting as much of the resources they might want later. So I'm just wondering if you sort of consider the joint objective of wanting to get rid of your jobs fast and therefore wanting to give them a larger allocation, sort of as compared with the objective of fairness. If you try to sort of balance these two things, do you think that your results would extend at all to that sort of joint objective?
So the question was, if I start doing things closer, I guess, to the scheduling literature, where I have arrival and departure times, and I have some quota I have to fill, or I have to use this much resource, or something like that. How would this come in play? How would the results change? Because as it was pointed, if I'm using less of resource, I'm going to take more time. So maybe it's better to be a little bit more unfair, but finish faster. So like this by objective thing is overall better. I don't know. I have no idea. all these are great questions. I know very little. I was just trying to study, fairness versus disruption. It's already a little bit of a mess, but all these are amazing directions.
So you considered the notion of maybe instead of disruption being this binary cost, right? If I interfere with one person, it costs me 1 unit. If instead I take away an X chunk of his resource,
I see. I'm disrupting more. So it's not the same if I take...
The more I'm taking away,
the more disruption it is. No, we haven't thought of that either. That's also a good question. So the question was, the suggestion was, maybe it's more disruptive to take a 0.1% of what you have than 50% of what you have. I don't know how that would change the results.
So also on that note, I guess, like if you're assigning like memory, right? Like you probably want to do it contiguously. So,
yep.
Is there any like study on what?
Good. So that I know partial answer to. So sometimes we can do it contiguously. So I think if it's all ones or all D, I think. Wait. Let me take that offline, actually, so I have 10 minutes to think about it. But I think sometimes I know the answer. So if I want it contiguously, that's a big issue in actual systems, right? Yeah. Sometimes I know the answer. I think with the zeros, I definitely don't know the answer. I think if it's all ones or all Ds, I think I might have something.
Well, if it's all
I have to think about it.
Like you can just do the same thing. You just steal from the person with the most, right?
Yeah, but you stole from the most, and then the most shifted, and it's in the middle. Then eventually the person who you're just giving to is going to become the best. It's not clear. Actually, you're right. Sorry. You're absolutely right. I'm thinking of a different algorithm. You're right. Yeah, that's correct. If it's all ones, I can do it. If it's all Ds, can I do it? No, I shouldn't be able to do it. Yeah, I think if it's only all ones, I can definitely do it. You're right. Thanks.
Anyone else?
I
I think the rest of the questions can be taken offline at this point. You drilled Alex long enough. All right. Thank you.
Thanks, everyone.